Okay. Okay, am I on? I'm on. Yes, good. Step one's done. So this talk's called Custom Layouts in iOS 16, and you might know I write the site Hacking with Swift, and I spend a lot of my time thinking about Swift and SwiftUI and so much more. And so when the SuperMinds team reached out and said, listen, do you want to come to Zagreb and speak? I was like, I could do that. And then they said the two magic words I most want to hear. First, we want SwiftUI, and second, we want something really technical. Like, yes, I'll be on the first flight out there. Let's do it. Now, this is actually my very first time here in Croatia, so I thought, I'm visiting for the first time, I've got to know, if there's one food I should try, what's it going to be? And I'm like, okay, I'm going to Google it, I'm going to Google Maps, TripAdvisor. I have the answer. You may not agree. Cevapi and Shishivapi is excellent food. There's money to be made. I trust you. Go and sell it abroad. It's amazing, good stuff. Anyway, enough about food. SwiftUI. Let's go back to the early days of SwiftUI. Okay, we know basic SwiftUI stuff. If we have three views stacked one above the other, we would say, well, this is a VStack because they're going vertically. Put those same views horizontally, we say, well, that's a HStack because it's horizontal. This makes sense so far, you with me so far? And put the same views one above the other. That we call a ZStack or a ZStack because of Zepth or something, I'm not quite sure what. But it means the same kind of thing, one above the other. And we could make an example view to show this kind of layout off. Example view like this one, we could say it's got some kind of color attached to it. And then its body, I'm going to say, has a rounded rectangle filled in with that color, and then has a fixed frame and a little bit of jiggle to it so you can see it more easily in a ZStack. Now, with that in place in Xcode, I can say, let's ditch the text hello world and write a VStack with four colors, red, green, blue, and orange. And boom, there we go, lined up vertically. Change the V for a H, and they become horizontal. Change the H for a Z, and they go one above the other. Now, I know what you're thinking. You're thinking, Paul, we know this is a while ago, right? Yes, but every year something magical happens. Apple come along and say, we've got a whole bunch of new things that totally hose your project, new ideas, new APIs, new ways of thinking to make your code different. And you can ignore that. You can totally ignore all the new APIs, and trust me, I know ignorance can feel great at first. But you're going to learn things, and you'll think, oh, I regret that choice. That was a bad idea. And so I'm going to talk about the new things this year, in particular this, AnyLayout. This is designed to be a type erased wrapper around another kind of layout. And you're probably thinking, well, that sounds like any view. And we've been told really, really clearly, any view is bad, any view has performance problems, any view, just avoid it. And then you see the code, and you're like, well, that even looks like any view. Why would I want to have any layout? And if there's one thing you take away from this talk and nothing else, it is this. Any layout good, any view bad, to summarize. And to see why any layout is good, here's what it does. We can change the layouts between VStacks, HStacks, ZStacks, and more freely. But we have no problems with destroying state when they change. All state of those subviews stays intact as you move. It does not recreate the underlying platform view, so your UI labels or whatever you're working with do not get destroyed and remade every time. You don't get janky animations moving between them. It looks fantastic. And there is no performance cost, unlike any view. Any layout good, any view bad. And in this case, we could take our current code, the ZStack and so forth, and add as a property to our content view a whole bunch of these any layouts in an array. So any layout, VStack layout, HStack layout, and ZStack layout, all in a single array. Then add a property to store which one of those items we're currently viewing. So index 0 by default, the VStack layout by default. And then add a computed property to store the currently active layout. Read my array, at that position, send it back. Now down in our code, I can wrap our current ZStack inside a VStack with some spaces around it, neatly spaced. And add a button that will change the animation, the layout every time, again and again and again. Whenever it's pressed, add 1, then loop back to 0 again, add 1, back to 0 again every time. To make it easy to see, I'm going to add a maximum width height as well. So it'll fill the whole area with a gray background color so you can see what's happening here more clearly, albeit without video. And when I change this single ZStack to be our current layout, it'll now jump to be vertical because it's VStack by default. That's the default 0th item in our array. But when I press the button, it will animate smoothly to be horizontal or animate to be overlapping with no extra code. And again, all the state of those subviews remains intact. So we have these layouts happening here. You've seen the names VStack layout, HStack layout, and ZStack layout. These are newer, different versions of VStack, HStack, and ZStack. And they're there for a reason, because internally they behave very, very different. There's all the old view builder stuff in VStack and so similar, and the new ones use call as function, and so the Swift compiler was really struggling to tell which one you meant with the old names. And so when you want to switch layouts, you want to use the extra word on the end, the extra layout word, just when you're using any layout. Otherwise, keep the old VStack, HStack, and ZStack. Now, as well as these three, we also have grid layout. And it's got the word layout in. This thing conforms to the same protocol. We can use this thing with any layout just as well. So in our code, we can say, here, we've got those three things. Let's add a grid layout as well. And now it'll animate. We're going to have 2 grid rows as well, say where the grid rows are. We've got vertical. We're going to have a horizontal, hopefully. There we go. Oh, and ZStack, and now also in a grid. And that is, I think, the only time in my career I've had the Windows logo on my presentations. Now, brilliantly, these grid rows become inert. They do nothing automatically when using the VStack, HStack, and ZStack. It doesn't mean anything there. It only means the grid layout has a meaning. And so we can intermix grids, vertical, horizontal, depending on the exact layout you want in your apps, with animation and state preservation. It's really, really awesome. That is my idea of good SwiftUI code, quite frankly. Now, these 4 all work because they come from the layout protocol. And the layout protocol is a single thing that defines the geometry of some kind of views. We can make our own. I do think it's fun. I also happen to like mathematics. If you don't, this might be a rather challenging talk for you. Now, to conform to the layout protocol, you've got to add 2 things to your view. You've got to tell it, when you have this much space available, how much do you want? How much space do you actually need for your subviews? And secondly, okay, I know how much space you want. Please now place all your views where you want them on the screen. Now, this first one is done with a method called size_that_fits. And you'll be told, okay, here is how much I'd like you to use. And here are your subviews to lay out. You can have a cache if you want to optimize things a little bit. And your goal is to return a single CG size of the result. Here's how much space I actually want. For the second thing, now we know how much space you want. Please go ahead and place your subviews where you want them on the screen. Then with place subviews method, you give them the exact bounds you want to draw inside, the real frame now, plus the original proposal that made that frame, and the same subviews and the same cache. So those 2 things. Add those 2 and you get a layout working. I'm going to demo this with a radial layout. A radial layout has a goal of projecting our space out like a circle and then placing views somewhere on that circle around the perimeter. That's its goal. To do this, we can go ahead and make our radial layout conforming to the layout protocol. And when you do so, Xcode is going to say, well, you don't actually conform to layout, sorry. So we can just go ahead and use the fixit to say, just give me some method stubs. Something that basically makes my code compile for now. We get here. Size_that_fits. How much space do you need? In our case, it takes us 1 line of code. We can say proposal replacing unspecified dimensions. And that 1 line of code completes that entire method. It's doing lots and lots of work. Now, to understand what it's doing, I want to go back again to the beginning of SwiftUI, to the 3-step layout process of SwiftUI. Step 1, the parent proposes a size for its child. Step 2, based on that proposal, the child then chooses its own size, and the parent must honor that. Bigger, smaller, has to obey what the child says. And third, the parent then positions the child in its coordinate space somehow. Now, what we're saying here is, this is actually in step 1. The parent's proposing a size for its child. It's saying, here's how much space you can have. And that might be a very specific size. It might be 500 by 500, for example. It might be somewhat vague. You can have 500 wide, but I don't really care how big you are. Or it can be completely vague. Actually, just be as big as you like, I don't mind. Now in Swift, we don't say unspecified. The absence of a value in Swift, we call nil. And so, when we're saying replacing unspecified dimensions, we're saying wherever there's a nil in there, just put a number in there. The default value is 10. It'll just take all the nils out and put something in there. So we can be guaranteed the result is a real CG size with a real width and a real height. In the case of our radial layout, we're effectively saying, all the space you've got, it's fine. I'll take it all. It's all good. And so now, back in our code, we have place subviews. This is more challenging. How do we place our views neatly distributed on a circle? This is where we'll learn which of you slept through high school mathematics. I've broken it down to 6 very small steps to make it as clear as possible. The first step, we're given a bounds. Here's the actual rectangle you've got to draw on the screen somehow. That's our drawing space. And our job is to put inside that drawing space our circle, to fill that space. Now we want to put one of our views on the perimeter of that circle. And that we call the radius. This is more sort of like 5th grade mathematics, maybe than high school, but we'll get there, don't worry. The radius, and so our step 1 will be get the radius of our circle. The minimum of our bounds width and the bound height is the diameter, and then halve it to the radius. Second step, we've got to figure out how to place another view after the first one. We've got to figure out what's the angle between the first view and the second view, and the third view, fourth view, fifth view, sixth view, and so forth. Now we know, I hope, there are 360 degrees in the circle, and we have n number of subviews here. And so it's simple enough, we can say the angle here will be 360 divided by n in radians. That's step 2. So we can say, there's our angle. Angle between each view on the circle. Step 3, we've got a whole bunch of views replacing, right? And it'll tell us, well, that's angle times 0, and that's angle times 1, angle times 2, angle times 3, and da-da-da-da. More generally, that is angle times I. It's index into the subviews collection. That's where it exists in the collection. Now, we can do that. That could be angle 0 if you want to. But a lot of folks will say, well, for me, for users, angle 0 is really straight up. So if we subtract half of pi, 90 degrees, we get angle 0 not being on the right, but being directly up. And now angle 1, angle 2, angle 3, and so forth. That's step 3. We're halfway there. Next, step 4. To get from our center to any of these places we've calculated in our circle perimeter here is a movement, a straight line from a circle to that view. Of course, really, this is 2 movements. Some movement horizontally, some movement vertically, combined to a diagonal line. And this, of course, x and y. We can get the direction of our x movement by using cosine of our angle. This is the high school part. I see you zoning out. And the y movement will be the sine. Sine of our radius and cosine of our radius. No tangent, I'm afraid. So we can say, get the cosine of our angle for x and the sine for our y. That's step 4. That's a direction to move in to find that place. But we need more than a direction. We also need a distance to get to the edge of our circle. So step 5 is multiply that by our radius. And finally, Step 6, we don't actually want views to be on the perimeter of our circle. What we really want is them to be just inside the circle, so they aren't clipped off the sides of the screen. That would look strange. And so we'll just subtract half the width and height of our views. And that's step 6. Whew. Come for the Swift, stay for the math. We can now say, in our Xcode, loop over all the views we have. Give me the index and subview for each one. We'll then ask the view, how much space do you need? And I'm using an unspecified proposal here, which means I don't actually care how big you want to be. Just tell me, and I'll make you work somehow. We can then say our xpos and our ypos. The y is the same. We just change cos there to be sin and width to be height. Now, a reminder, how much space to move around for each circle is the angle. This is our position in the collection. Multiply together, how much to move around the perimeter for this particular view. Make 0 degrees go upwards. And then the whole thing, tell me the correct x direction for this finished angle. We then know how far to move to the outside of the circle. Bring it back in so we're always inside the circle. And finally, how much x to move so this circle appears on the edge of our perimeter, just inside. Okay, that's x and y. And now we can go ahead and make that a CG point and call subview.place. Now, these last 2 lines of code, the top one here was saying, position this view relative to my circle center. If you don't, it'll be the top left corner of your view. You get a sort of fan effect where 3/4 are completely off the screen. And the bottom one is saying, we're placing the center of this view. Center yourself here, please. But I don't care how big you are. Be as big as you like still, it's fine. And with that, we finish our radial layout. So we can go ahead and say in our content view, scrap that code. Instead, there's a view count. 8 by default will work. But it's state, so it's locally modifiable. I'll delete all the body code and replace it with a radial layout, counting from 0 up to our view count. Each time drawing a circle with a 32 by 32 frame. And below that, I'll place a stepper, so we can move up and down, with technically animation, but not here. And you can see already we have 8 views spaced neatly around a circle. But as I change the stepper, the new ones will animate in flawlessly up to, in my case, 36. It'll just fit them all in equally every time. So that's the layout protocol. It'll tell us size that fits. How big do you want to be? In our case, actually, I just use all the space you've got. I don't mind. Give me all. I'm a circle. I'll just grow and grow and grow. And then it'll say, OK, now place with subviews. Great. We'll just go ahead and calculate angles around and place them all there. That completes a radial layout. It can join our friends. Grid, ZStack, HStack, and VStack layout. And they all have layout in there for a reason, because they all conform to the layout protocol, which means they can all go inside any layout. And so we actually go back to our Xcode, press undo once to get our old code back. And when we do that, we can now add a radial layout to our array of other layouts. And now we have vertical, we have horizontal, we have ZStack, grid, and also radial layout. It just plays along beautifully with the alternatives. So that's radial layouts done. How about we try something harder? Now, we're going to try a masonry layout, creating uneven kinds of views like this one. How do we place this kind of thing? And the answer is, you'll love this, mathematics. But I've been told ahead of time, you folks know what's up with maths, you'll be good at this, I'm sure. If you aren't, the exit's just over there. So, it's called masonry because mostly in straight lines, but many of the views are sort of jagged. They have different sizes inside the masonry. And it starts off relatively simple. New masonry layout conforms to the layout protocol, and this time we're going to say how many columns we want to have. 1, 2, 3, 10, potentially on a Mac, who knows what. Some number of columns. We'll also allow a configurable amount of spacing between our views, horizontally and vertically. and we'll add a custom initializer with default values. Why? I want to make sure there's at least one column, always. 0 columns minus 1 column. Doesn't make sense. Always at least 1 column. OK. If you put it into Xcode, unsurprisingly, it does not implement size it fits and so forth. It does not conform to the protocol. Big warning. I'm going to insert placeholders again. I'm 0 size, no subview placing, whatever. Just go away compiler errors, basically. Because I'm not going to write these 2 methods first. Instead, I'm going to write a helper method called frames for subviews in total width. And this is the job of taking all our subviews plus the width we were allowed to use, and it will return an array of CG rects. It will return all the frames for all the views in one pass. And now we can start making some constants. We can say, well, the total spacing between all our views is the spacing constant multiplied by 1 less than our column count, because it's spacing between the views, not outside the views, just between the views. So 2 views, 1 space. That's our spacing. Second, our column width. How wide can one column be? Well, that's a matter of doing our total width minus our spacing divided by our column count. Next, column width with the spacing, makes the math slightly easier later on, is column width plus spacing. And now the proposed size. How much space do we want to give to one of our column views? And it's going to be that column width with a height of 0. We're saying you've got to fit in this space if possible, but you can grow as big as you like. I just don't care. So now we'll make an empty array for all our view frames. We'll fill this up one by one as we size our views. And we'll also make an array of column heights, how big all our columns are. We have column count, but they're all starting at 0. And the reason is because of the way the masonry algorithm works. Imagine a layout stuff like this. There's your layout. You've got 3 columns, for example. The layout will say, well, these things all have 0 height by default. They're empty by default. I want to go ahead and find the shortest one. And it'll go through. Is it you? Is it you? Is it you? And initially, they're all 0. So the first one's fine. So it'll choose that one. And it'll place a view there and say, OK, I've sized the view up. Your height was 50. That column height is now 50. The next view that comes in, it'll loop again. And this time, well, it's column number 1 is the shortest. Still column index height 0. And it'll add a view there with 80, for example, and place that there. And placing a third view. Well, OK, fine, it's the last one this time, so that's now got a height of 20. It's still the shortest column. So when the 4th view has to be placed, fine, put in that one too. It's now 70. So next time around, it's 50, and so on and so forth. So our goal is to go ahead and loop over all the subviews, calculate them one by one, their size and their heights, and finally return that view frames array. So step 1. When we begin, we're going to use column 0. Assume that's the right one. And we're also going to say the best height we have is the biggest possible double. Every column is shorter than that, basically, but it's an initial value that's guaranteed to be overwritten. And now we can loop over all our column heights and say, well, is this column height less than our best height? If it is, you are our new best column and our new best height. When we finish this loop, we now know the best column. It's selected column here. So we can find the X position for our view by multiplying that by column width, including the spacing. And the Y will be whatever height is that column right now. That's X and Y. For the size of the view, this time we're going to propose the earlier proposal. The width of one column, height of 0. You've got to fit in one column. I don't care how tall you are. But there's an asterisk here. We're saying, please, try and fit in one column. We can propose a size. It's down to the child to say the size they actually want. They could go, nope, I want the whole screen. That's their prerogative. It's a request, a proposal. So with that now as size, we can say, OK, I've got your frame, X and Y, your size width, your size height. That's your finished frame. We can now modify our column heights array. For the column we just placed a view in, you are now bigger by the height of this view. And finally, add that to our view frames array, which then gets sent back. And that's our helper method. Does nearly all the work we need to make the whole rest of this layout just work. And so in size that fits, first we have a proposal. Here's how much space you can have. Might have some optionals in there. So we'll start by saying, well, our width is going to be that proposal with all the unspecified dimensions replaced with real numbers. Give me the width back out of that, please. Then we call our helper. Give me all the view frames you have here. Everything all at once. We'll then go ahead and find the highest value in this thing. Now, max here is saying, sort this array by maximum y. So it'll mean the last version, the highest thing here, the highest view frame is the one at the lowest on the screen. Or if there's nothing in there, return 0. And finally, send a CG size back with the width of chosen plus the maximum y of our maximum lowest view. And that size that fits. In place subviews, again, call our helper method. Does all the work for us. So we can now loop over all the subviews we have, get the frame out from our array, calculate that offset from our top left corner, because our collection could be somewhere on the screen, we don't really know where, and then place it there, using the proposed view size of the size the thing's supposed to be in the first place. Fit into the space you said you could fit into. So for our masonry layout, we have size that fits, which is now saying, okay, the width's cool, I'm good with that, but my height needs to be the bottom of the bottommost view we had trying to place here in the first place. And then place subviews, fine. We know all the frames ahead of time, just place, done. Now done again. We can go ahead and put it in practice. We can make a new example view, this time fractionally more complex. It's got a size, but also a color to work with. And we'll say there's a ZStack with that color being shown, but also some text. So we know how big this view ought to be. Show me the size, the width and height I request you to be. Now this view will be scaled down or up depending on our column count. And so we'll make this text flexible. We'll say, you've got to fit across one line, but you can go down to half your size and do a nice chunky font so you can hopefully see at the back. But critically, we're also going to attach an aspect ratio to the whole ZStack. So it can get bigger or smaller, but always stay the same aspect ratio the entire time. And now in our code, we can say, make a whole bunch of colors, blue, cyan, green, my favorite's mint, by the way. Track the column count for our masonry layout. And then make a whole bunch of view sizes. Store the states so they stay alive as we're animating things around neatly. And each size will be a random number between 100 and 500 width and height. So lots of random sizes. Then our body will do a scroll view this time, because it could be a lot of views being displayed. But inside that's our masonry layout with the column count we asked for. Then loop up to 20, placing an example view of the correct size, and one of the colors using I modulo the color count. Bit of padding. And then add a stepper so we can control the column count dynamically. As a background here, because it will overlay the scroll view. And when that's done, this is the result. Completely flexible view layouts based on the size they were requested. And as you change it, I have no animations here, I'm afraid, you'll see it dynamically moves across to the new layout wherever it needs to be. It's very, very flexible. It's 2 columns or even 1 column. It'll resize dynamically. So that is the layout protocol. Size that fits and place subviews is extremely powerful stuff. There are more things you can do with it. You can do layout caching. You saw in-out cache, empty tuple, empty void. Just means there's no cache there, but you can add a cache. If you're doing really computationally expensive layout work between these two methods, reuse the work. You can do custom animations. Perhaps you want your views to slide out or move around in a neat way rather than just moving directly in a straight line to their destination. And you can even use view priority. Oh, this view wants more space or less space. Adapt my layout dynamically. Now, I've got a handful of tips for you. Firstly, caching is easy. You probably don't need it. Honestly, this stuff is extremely fast. I haven't had a problem at all, not once. This is partly because when you are calling things like size that fits, it's being cached by SwiftUI. It remembers the size that came back in the request you made automatically. So you get some degree of caching for free. And of course, the cache, you've got to invalidate the cache. Change it at the right time, otherwise, oops, they rotated it, it's broken now, who knows? So you're creating pain for yourself. Second, size that fits can be called many times. And it might be, firstly, oh, here's all the space, how big do you want to be? Or perhaps, here's hardly any space, how big do you want to be? Or here's nothing at all, what's your ideal, your intrinsic size? And you can basically query the view and learn about the view you're working with and make it flexible around different choices. So when we see place subviews, this is why we're handed both the bounds and the proposal that made that bounds. Because our own size that fits method could have been called many times. How about this? How about this? How about this? Eventually, one of those will be used. It must use one of them, and that will be the bounds. But it'll remind us, oh, by the way, here's a proposal I gave you that made you return those bounds. Next, subviews, the collection we had, conforms to random access collection. We placed our radial layout going clockwise from 12 o'clock onwards. You can do what you like. Place them in any view order you want to. It's down to you. It's zero-based, it's contiguous. Go for it. Fourth, you can customize the direction of your thing. And this is not just about changing the layout, it's about changing the way SwiftUI understands it. For example, particularly dividers. Now this is saying here, it's a static method on our layout, I am a horizontal layout. It's vertical by default. So when you place a divider in a vertical layout, you get a horizontal divider. This says, oh, I'm a horizontal layout, give me vertical dividers. It does matter. And finally, you probably don't need caching. You really don't. It's extremely fast. If you have profiled your code and seen for sure, yeah, this is definitely a real problem, fine, implement caching. Otherwise, do not go near caching. It's faster than you think. The biggest tip of all, I wrote a new book on SwiftUI called Pro SwiftUI. It's 2 weeks old today. Go to that link. You can get it 20% off. 5, 4, 3, 2. It's Bok Zagreb. Come on. That's the only Croatian word I actually know. It's Bok. I'm good at Croatian, me. And I do have some stickers if you like some after on. Anyway, that is custom layouts on iOS 16. Thank you very much.
I have maybe a technical question. One of the parts in deciding the child's size view is where the parent proposes the child size, right?
Yeah.
But then the child can completely ignore the proposal. So what's the point in proposing at all?
So many views in SwiftUI have a built-in intrinsic content size. How much time do I have, by the way? I could go and talk about our SwiftUI.
No.
So SwiftUI has exact ideas of what something should be in size. Like some text, for example. The text will be the exact width and the exact height to display the characters it has, ideally all on one line. Bok, one line. Complete works of Shakespeare, one line. That's what text likes to have. It's ideal width and ideal height. Okay? But it's flexible. It has no minimum height or minimum width. So we can crunch our text views down and down, down, and it'll adapt, right? On the flip side, it has got a maximum width and a maximum height. They're the same as the ideal width and height. It likes to be exactly enough to hold its text on one line, that's it. No amount of futzing from us to make it bigger than that. You just cannot do it in SwiftUI. You can add frames around it, but the text never changes its size. The flexibility is the problem, or the power of SwiftUI. It could be complete work Shakespeare, one line, or perhaps across multiple lines, and so we call size that fits multiple times. You say, hey, how would you be when you're small? How would you be when you're bigger? How would you be when you're exactly this big? We can go, actually, I can make you smaller and make this bigger, and so it gives us the chance to say, okay, based on what you've told me, I can see that. I can make you smaller and give more space to something else to make my layout better. And you'll see this with HStack, for example. HStack, by default, if it has 2 views to have flexibly infinite widths, it'll be exactly half in size. But if they weren't flexible, it'd say, well, actually, you're less text in this one. I'll give this one more space than this one. It's sizing it carefully along the way. That's what it is. Hopefully it helps.